Welcome to this lecture. This is the final lecture of this course. We have already covered the content in the previous lecture. The goal of this lecture is to summarize whatever we have learned in this course. Let us move on to the slides. So in this course, our target, as already mentioned in the introduction, was to learn about the mathematical foundations of probability. And to do this, we learned about measure theory and have gone over these following topics in detail and not necessarily in the order listed here. Okay, so we are listing certain topics that we have covered, but these topics are not discussed in the order in which it is listed here, but this is just to summarize whatever we have learned. The first thing that we have covered is the structure of the collection of events of a random experiment, and then more generally we looked at the structures on collections of subsets of a given non-empty set, and these structures were in terms of fields, sigma fields and monotone classes. Next, we studied the size of these subsets, or respectively the possibility of occurrence of these events through measures and respectively probability measures. So for size of subsets of a given non-empty set, we looked at their sizes through measures, and for possibility of occurrence of events in a random experiment, we looked at the corresponding probability measures. Now, in order to quantify the outcomes of this given random experiment, what we did was that we discussed the concept of random variables and vectors, and more generally these were formulated in terms of real valued or RD valued measurable functions. Now, once we have understood these concepts of measurable functions and random variables, we then looked at the law of these random variables or vectors and found corresponding distribution functions. Now, once we had obtained these distribution functions from these laws, we looked at the correspondence in the form that given a distribution function, we constructed the corresponding probability measures. However, along the way, what we have finally managed to show was that there is a correspondence between random variables or vectors, their laws, which are probability measures on the appropriate dimensional Euclidean spaces, and distribution functions. So we had defined distribution functions independent of the connection with random variables or probability measures, but at the end we had shown that any distribution function is essentially a distribution function of a random variable or a random vector, or it can be thought of as a distribution function of a probability measure. Now, once we have understood these correspondences, then we looked at decomposition of probability measures on these Euclidean spaces RD, and accordingly a similar decomposition was also discussed for corresponding distribution functions. Consequently, what we did was that we obtained discrete, singular continuous and absolutely continuous distribution functions. Now, probability measures that corresponded to these special classes of distribution functions led to familiar type of random variables or random vectors as seen in basic probability courses. For example, we had connected it to the discrete random variables and absolutely continuous random variables. Now, an extension of this above correspondence that appeared between distribution functions and corresponding probability measures was discussed, and these connected these Lebesgue-Stieltjes measures on Euclidean spaces with non-decreasing right continuous functions on RD. So this was the extension of the original correspondence that we found between probability measures and distribution functions. And as a special case of this correspondence, we had obtained this special measure called the Lebesgue measure. Then, after understanding all these different examples of measures, we studied the measure theoretic integration, and as special cases of this integration, we had covered the following cases. The first was expectation of random variables as an integration with respect to the corresponding law. So that was the first thing that appeared as a special case of measure theoretic integration. But then we have also studied the connection between Riemann and Lebesgue integration, and finally putting together this knowledge we had been able to compute the expectation and more generally moments for discrete and absolutely continuous random variables, and the formulas that we obtained matched with those expressions as seen in your basic probability courses. So with these topics we have covered the mathematical foundations behind probability, and hopefully this will be useful in your future studies. But now, as a follow-up of this course, you may consider reading about convergence of sequence and series of random variables, or stochastic processes in discrete and continuous time, and about applications of probability in other areas of mathematics. I hope that you have enjoyed this course and that this course will be helpful for your future studies. Best wishes on your future endeavors. Goodbye for now.